it's a controversy among philosophers. That started with the Scottish Enlightenment philosopher Charles Hume, who suggested that it's impossible to observe causation. Yeah, if we see this a pencil falling to the ground, we make a hypothesis about why this happened. Of course, we know that it's gravitation, but we cannot directly observe gravitation. We assume that the fact that if I lose control over the pencil and it falls to the ground, that this can be attributed to the causal effect of the gravitation. Yeah. But the only thing that we can observe is the regularity of the event. Yeah. If you do this with other things, of course, they will also fall to the ground. It's a regular association between a cause, yeah, and a succeeding effect, and that's all that we can observe. We cannot observe causation directly. That is Hume's position. Yeah? Implied in this is the notion that it is impossible to see an effect if the cause is absent. So this counterfactual nature of causality. You have causation. If there's no cause, then you shouldn't have an effect. If you would have an effect, if there's no cause, then there's no clear causation. Then another notion of causality that has developed is from experimental research. If we deliberately manipulate a cause, increase the pH value of a liquid, then we might observe certain reactions, for example, in chemistry. And then in a somewhat different way, other philosophers have insisted on a mechanismic understanding of causality. That is very well possible to observe mechanisms that link causes and effects. But it's not necessary to have a regularity, as Hume assumed, but it is sufficient to understand the mechanisms. That's a different epistemologic notion of causality. It has been suggested in the philosophical debate, in the debate among epistemologists about the nature of scientific knowledge. Yeah? And this is partially congruent with the distinction between what is termed probabilistic causality and deterministic causality. Probabilistic means that we assume that there's always random, there's always coincidence. We cannot fully explain everything because it might simply happen by chance. Yeah? If we throw dice, for example, there's a lot of chance in it that we get a 6. Yeah? But obviously, from a regularistic or from a probabilistic understanding, the more often we would throw the dice, the more likely will it be that in some 1/6 of the cases we would get a 6. Because the distribution, if the dice is of course a fair dice, and the probability that we get all the results is equally high, then we know fairly well, if we just throw the dice often enough, that we will exactly get that result. Other researchers have and philosophers have advocated a deterministic understanding of causality, where they argue that randomness and chance are not systematic features of reality, but simply due to our limitations of the observation, and perhaps also due to the imperfect models that we have of reality in our minds. This more deterministic version leads to the understanding of causality that is probably prevalent in so-called qualitative social science research, whereas the probabilistic idea of causality is typical for quantitatively inspired type social research. So it's important to see that these controversies that we have in the social sciences today between so-called number crunchers, yeah, those people who like to work with numbers and to show associations using statistical methods, and those who like to stick to cases and like to give dense and detailed descriptions of these cases and come to conclusions on this basis. These controversies are rooted in an epistemological controversy among different types of causality. Yeah, the probabilistic causality is somehow rooted in the Humean understanding of the regularity as the only thing that we can see. It's impossible to observe causation, whereas the other understanding of causality, the deterministic one, assumes that it is possible to observe and to prove that these mechanisms are indeed the causes of the effect. Now, I suggest a definition of causality I took from a social science methodologist in the US, John Gehring. He argues that, and this definition of causality, that would fit both the probabilistic and the deterministic idea of causality. He argues that a factor is the cause of an outcome. The factor is called X. The outcome is called Y. If a change in X generates a change in Y. Relative what Y would otherwise be. So if we don't have X taking that value, we would not expect the particular outcome of Y. Given certain background conditions. Yeah. In the case of gravitation, that's quite clear. You have to be on the Earth. Otherwise, elsewhere on other planets, what you throw to the ground would not fall so quickly to the ground, for example. Or maybe quicker if it's a bigger planet and so on. Yeah? That would be one important background condition. Or in the case of our example of the business elites and the political elites, one background condition could be for example, the size of the economy simply. One could argue that a larger size obviously generates a larger business community, and it's much harder, much more difficult to coordinate with this business community than if you have a small business community where the connections between the individual people are closer, and this necessitates other perhaps techniques of political control and political rule. Causality also usually implies certain scope conditions. That is, to what extent one can generalize to a broader population of cases, a broader set of cases. We often use these terms independent and dependent, exogenous and endogenous variables, particularly in quantitative research, but qualitative researchers also tend to use these variables. Usually the independent variable is the variable representing the cause, and the dependent variable is the variable representing the outcome. For the moment, I think, this is basically tantamount with the distinction between exogenous and endogenous variables. We come back to this. Now, this is a basic causal diagram that Gehring has suggested. Here you find again our letters representing the variables. X would be the causal factor, otherwise also called explanatory variable, independent variable, the intervention, the predictor, the treatment in medical studies, for example. Yeah? Those are the people that get the pills, the others do not get one or get a placebo, perhaps. And then epsilon is the outcome variable, the effect and the response variable. One group dies or has a lot of, in the medical research case, dies perhaps or has a positive health effect, and the others do not have such an effect. And M is the causal mechanism or process, the intermediary, sometimes also called intermediary variable, between the cause and the effect. And then often we also have antecedent causes, prior causes, that influence the value of the causal variable. You mentioned this already initially in our brief conversation about the role of the business communities, that obviously different pathways of privatization might have mattered for the way the relations are structured between the business elites and the political elites. That would be perhaps such an antecedent cause. Then we have other causes of epsilon, and we have so-called confounders. The problem that we usually face is with these confounders in our research. Yeah? To clarify to what extent we can isolate the causal effect that we want to prove and that we want to show and we want to argue from other possible causal effects that are also somehow in the play there, and that influence perhaps the values of x and also the values of epsilon, and it's often very hard to distinguish between the c and the x. So these confounders cause the problems for us. In an experimental setting, it's easy somehow to control the confounders, because people are then locked in a room, for example, and they have to do precisely the same questionnaire, and we make sure by selecting the people that we want to have there that we don't have disturbing influences. But obviously, of course, the limitation of such experimental research, which is also nowadays increasingly practiced within political science, for example, or social sciences, is that it's often very hard to infer from these laboratory situations to the reality. Good. That's the way Philipp Schmitter has visualized it. You start from the idea. We talked about conceptualization based on the example of the business-state relations, generation of hypotheses. We saw these different rival hypotheses. Then go to a case selection. I mean, the way I presented it was that I started with the cases that would interest us. And very often, of course, you have cases in mind, but in research design, it's important, of course, to legitimate to yourself and to the community of researchers and to the broader public why you have chosen certain cases, why the chosen cases are particularly relevant. Yeah? Why you think that your selection of cases is ideally as the best, as the second best solution next to an experiment. Yeah? Then sometimes in research you have to write proposals to participate in a PhD program or so, for example. Then you go on to operationalize your variables, look at possible indicators, and then the measurement takes place, and then you might get surprised. It's the word serendipity here, surprise findings that might cause you to throw your initial concept overboard and develop a better one. Yeah? Simply because you note that the reality is not as I would have expected it to be. Then you test for the association between the variables, the causal effect, either in a qualitative or in a quantitative way. And then you try to generalize your findings to make a statement about the causal effect of your variables. And then, of course, it's conceptualized, it's visualized here as a circle. You have learned something from the research, perhaps. This leads to a self-assessment, and you might then refine your topic and develop other avenues of research and go on.